Greeting, my name is Ge Baoyuan. Today I'm honored to present my proposal titled A Comparative Study of Machine Learning Model of Binary Sleep Quality Classification. First of all, I would like to briefly outline the structure of my presentation. Today I will talk about 6 parts in turn, and here is the content. Now let's start with the first part. Today's society. There is a rising problem about extensive use of electronic devices, the high stress level in daily life, and sleep quality issues. Poor sleep quality is closely associated with a series of problems, even have negative effects on physical and mental health. Currently, research on sleep quality prediction mainly relies on 3 approaches: wearable devices, mobile applications, and questionnaires. These methods collect a variety of sleep-related data. However, there are still 2 key questions that need to be addressed in this field. Therefore, this study set 2 core research objectives. First, among 6 commonly used machine learning models, which one is the most suitable for binary classification tasks of distinguishing between good and poor sleep quality? Second, under the same set of input features, which variables contribute the most and serve as the key factors in differentiating good sleep from poor sleep? The research has important significance in 3 aspects, including methodological, application, and practical significance. And the research will follow the systematic process as the picture shows. Before introducing my research, let's review the previous related studies in this field. Existing research on sleep quality prediction can be roughly divided into 2 categories. First category uses questionnaires and scales, such as the Pittsburgh Sleep Quality Index, and the second category relies on high-cost physiological signal, such as polysomnographic data. Although these methods can be achieve high prediction accuracy, the equipment is expensive and the data collection is complex, making them unsuitable for large-scale promotion among the general population. Few studies have specifically identified the most suitable model and the most critical feature of sleep quality classification, especially under the permission of using low-cost, easily collectible indicators. This study has 3 main innovation points in order to improve these research gaps. Next, I will introduce the dataset used in this study and corresponding pre-processing steps. The dataset, which includes 452 samples and 15 variables. The main features cover 3 categories: demographic characteristics, sleep structure indicators, and lifestyle factors. Regarding data quality, the missing values are concentrated in 4 variables: awakening, caffeine consumption, alcohol consumption, and exercise frequency. In addition, the following 4 variables have extreme values. The specific data pre-processing steps are as follows. First, for the missing value, I use the median for numerical data gap and the mode for categorical data gap. Second, I perform binary encoding on categorical variables, such as gender and smoking status. Third, I select 11 feeders for modeling by deleting irrelevant variables. Fourth, I construct the target label based on sleep efficiency. Finally, I use certified sampling to split the dataset into training set and a test set, ensuring that the proportion of good and poor sleep labels is consistent in both sets. As correlation metrics of numeric features show that sleep quality has a strong positive correlation with sleep efficiency and deep sleep percentage, and a significant negative correlation with light sleep percentage and awakening. In contrast, The correlation between sleep quality and daily intake behaviors are weak. Next, the pattern shows that age follows a relatively smooth unimodal distribution, concentrated in mid-age range. Sleep duration is may distribute around 7 to 8 hours. Overall sleep efficiency is mostly above 0.8, and most individuals experience 0 to 1 awakening per night, with only a few samples have 3 to 4 awakenings. Furthermore, scatter plots confirm that how above factors affect sleep efficiency. First, there is a significant positive correlation shown in deep sleep percentage. Second, a negative correlation was displayed in sleep efficiency and light sleep percentage, and the relationship between sleep efficiency and awakening are negative. These results further verify the important role of sleep structure and nighttime awakening in determining sleep quality. In this study, I selected 6 classic machine learning models covering different modeling paradigms. First, logistic regression, a linear model. Second, random forest, an ensemble model. And other 4 models are decision tree, k-nearest neighborhood, support vector machine, and naive Bayes. Here is a summary of the advantages and disadvantages of 6 models, shown in the table. Each model has its own trade-offs. In terms of model evaluation, I adopted 4 commonly used classification metrics: accuracy, precision, recall, and F1 score. Their formula are as follows. These metrics comprehensively evaluate the model performance from multiple perspectives, especially focusing on reducing the risk of misclassifying poor sleep as good sleep, which is crucial for sleep health management. After completing model training and tuning, I obtained the performance comparison result of the 6 models, as shown in figure and table. Random forest and decision tree achieved the highest comprehensive performance, both with an accuracy of 0.9011, a precision of 0.8163, a recall of 1, and an F1 score of 0.8989. The difference between them lies in training time. Random forest takes about 0.67 seconds, while the decision tree only takes 0.0087 seconds. After considering the decision tree easily overfits the training data, random forest would be the best performance model. To further verify the key factors affecting sleep quality, this chart compares the average deep, light, and rapid eye movement sleep percentage between good and poor sleep groups. It shows that the good sleep group has a significantly higher deep sleep percentage and a lower light sleep percentage, while the rapid eye movement sleep percentage is almost the same. This confirms that sleep structure is an important determination of sleep quality. Here are 4 charts about factors lead to good sleep. The first chart about awakening would be the greatest impact factor. When there are 0 awakening, the good sleep rate is close to 100%. Once awakening occurs, the good sleep rate drops sharply to around 60%. The second chart shows the good sleep rate by deep sleep group. The 50% to 70% group and above 70% group have no much differences. However, the below 50% group, almost no samples are labeled as good sleep. The third chart shows that the high exercise frequency indicates a positive association between regular physical activity and good sleep quality. In contrast, the last chart shows that sleep duration has little impact on sleep quality. Based on the above study, I draw the following conclusions. First, among the 6 machine learning models, random forest performs the best in the binary classification of good or poor sleep quality, with high accuracy and recall, effectively reducing misjudgment and omission of poor sleep cases. Second, the number of nighttime awakening is the strongest single factor affecting sleep quality. Exercise frequency has a moderate positive effect, while other intake behaviors have relatively limited efforts. Third, compare with getting more sleep, reducing nighttime awakening, optimizing the sleep structure, and maintaining regular exercise are more likely to achieve good sleep. However, this study also has some limitations. For example, the limitation associated to variables and design. The dataset linking important factors such as stress, emotion, and environment. Moreover, it is a cross-sectional data, which can only indicate correlation but not improve causality. Finally, I would like to express my sincere gratitude to my supervisor for his valuable guidance. Thank you.